Hello, am I audible? Okay, good. Just a moment. Hmm. Okay, so hello everyone. I'm a PhD student at IIT Bombay and I study cryptography. And today we are going to discuss some questions and some questions that I have in mind. And in case you have anything in mind, you can ask me. Okay. So we'll start. We should start. I hope, yeah. So my screen is also visible. Okay. So here's the first question. Yeah. Let P, C, and K denote the plaintext space, the ciphertext space, and the key space, respectively. Now we are thinking of a shift cipher, right? So what is a shift cipher? Uh, yeah. So shift cipher is a cipher in which, so if your plain text is B, let's say, right? That's a single letter. This is the plain text. And let's say the shift key is 2. Then the ciphertext would become D. This would be ciphertext. So you shift B to D. So you shift B to two positions and you get D, and that is the ciphertext, right? So this is what a shift cipher is. Okay. Yeah. Just a moment. Okay. So in a shift cipher, the thing to note is that okay, yeah. So consider, so the question is consider the situation where P, C, and K are equal, and this is equal to Z26. So Z26 is the ring. Ring is a mathematical object. A ring of, sorry, so a moment. Yeah, should, okay. A ring of integers modulo 26. So what's a ring? So the elements of Z26, basically it's yeah, so the elements of Z26 are the integers from 0 up to 25, right? And each of these elements satisfies some operations. So you can do addition. So for example, if you have two numbers, let's say if you have two numbers, x and y, you can add x and y to get x plus y, but additions happen mod 26. So Z76 means that you can add two integers, but whatever the result is, it has to stay in this set, in this object, in this ring, right? So this is it, and zero is the identity. So if you add zero to any other number, you get the same number. So basically integers, but modulo 26. Okay. So consider the situation where the plaintext space P, the ciphertext space C, and the key space are all this ring, this object Z26 or integers modulo 26. Basically, you can also think of these as alphabets. So there is a one-on-one mapping between Z26 and the set of alphabets, right? You can say that 0 is same as A, 1 is same as B, 2 is same as C, and so on. And 25 is same as Z, the alphabet Z. So there is a one-on-one mapping between this set Z26 and the set of alphabets. Okay, so Z26 is like a mathematical representation of the set of alphabets. Okay, so uh, in the question, the plain text space, the ciphertext space, and the key space are all Z26. And suppose that uh, the shift key is equal to 6, and that the ciphertext equals 1. So the after we do the shift, after we do this operation, the result is the value 1. So the question is, what is the plain text? Okay, so I hope it's clear what the question is demanding. So in any, so I'll just recap things in case it's not clear. In any crypto system, there are three spaces, right? The plain text space, the ciphertext space, and the key space. So the plain text space is the starting point. So any the plain text will be -5, but remember that everything is happening modulo 26. So what is -5? Yeah, no, you're right. You are right. But modulo 26. So do you understand what this means? Modulo 26. Right. Yeah. So that is correct. You are right. The plain text, the answer is 21. That is true. So it's like you had 21, or 21 in alphabets would be, so 25 is Z, Y, U. Okay. Yeah. It's V. U, W, W, X, Y, Z. Yeah. It's V. Okay. Sorry. Yeah. Sorry. Sorry. It's V. Yeah. Yeah. So it's like, so just to uh, just for context, it's like you started with V, which is equivalent to 21 mathematically in the ring of modulo 26 integers. And the shift key was 6. So you added 6. You wanted to shift V by 6 positions, and you ended up with B, which you should, right? Because wrap around. So you started with V, W, X, Y, Z, A, B. So B is what you ended up with, and so what was the plain text? What was the starting point, right? So yeah, so it's not a very involved question. Like uh, if it's easier for you to think in terms of alphabets, maybe you could have started with saying, okay, you started with B, and what would have been the alphabet, so that adding 6 you would have gotten B. So A, Z, Y, X WV, right? Yeah. So there are two ways to think about it, either mathematically or uh, via the common reasoning ability, and yeah, you can end up with V both ways. So this question is to describe, like, is to bring home what a shift cipher is, what a plain text space is, what a ciphertext space is. So in this, so usually in a shift cipher, the plain text space and the ciphertext space are the same, right? Key space is, you can view key space differently, but the plain text space and the ciphertext space are usually the same, right? And key space is like shift, so it's basically integers of some kind. Yeah, so that's the main thing. I hope that is clear. And also, what is Z26 and modulo? It's so mathematically in computer science, especially in cryptography, this modulo notation, it comes up a lot in a lot of crypto systems. Even modern crypto systems, like these are very outdated examples. This is also called the Caesar cipher, the shift cipher. That is another name for it. And these are, yeah, and these are all examples of symmetric key crypto systems. So maybe I'm rushing ahead, but as long as you are understanding things, it's okay. Symmetric key crypto systems are where the same key is used for both encryption and decryption, right? So for this shift cipher, you add some shift value, some key during encryption, and during decryption, you subtract the same key. So the same key is being used in both processes, and that's why it's a symmetric key crypto system example. Right. There is a these are not secure, obviously, or maybe we'll get into that later. The more secure version, uh, yeah, the more secure version are the public key crypto systems, right, or asymmetric key crypto systems, which are used today. But like, forget that maybe. This is a symmetric crypto system, the Caesar cipher, and it's a very simple example. It's but still, like the modulo, this modulo terms come even in the modern public key crypto systems also. The more complicated crypto systems also work over some uh, mathematical space, and modulo operations come up a lot in cryptography in general. So I hope that is clear. So we can move on now to the next question. If anyone has any questions, feel free to ask. Vigerian cipher, the demerits. So we'll get to that later. Or maybe the better thing would be to read on Wikipedia. But yeah, let's get to that later. I have some questions to discuss uh, before discussing the Vigerian cipher. Okay. So another easy question. We are working with a shift cipher crypto system, same as the previous example, but this time with strings instead of just single alphabets. Now we are working with a string of alphabets, and the key is 3. So the shift is 3 for each position in the string, and the plain text is MATH, the string of alphabets MATH. What is the ciphertext? It's a very simple question, right? Uh, so I, yeah. What is the ciphertext? So you have a string of alphabets and the shift key is three, right? And you want to like translate every alphabet. Yeah. So P D W K, correct? Yeah. Simple question, but still just to get the point across. Uh, when you have a shift, you want to shift each alphabet, and there is a string. So you go one by one, and you translate M to P, A to D, T to W, and H to K. Yeah. Okay. So the difference here was the keyword was string, right? You have a string now, and uh, so for example, the most common representation in mathematics in theory that we talk about is the binary string, or you can also call it a bit string. So what is a bit string? A bit string is a sequence of zeros and ones, right? So uh, 0 1 0 0 0 1 1 1 and so on. This is an example of a bit string, right? And there can be, of course, many such examples. So if you have n positions and you want to fill it with zeros and ones, there are 2 to the n many possible bit strings on these n positions, right? Why bit strings? Because as simple as it seems, it's a complete model of representation in itself. So, for example, if you have this math, you know, this what we are used to usually when we study English, right? So alphabets, we are used to alphabets, but it could have been possible to have a very different education system and convey the same information, but using only zeros and ones without having to require the full 26 alphabets. For example, uh, okay, let me just convey this properly. Yeah. So let's do this properly. There are 26 alphabets, and 2 to the 5 is 32. So 5 length 5 bit strings, length 5 bit strings are sufficient to represent English alphabets. What do I mean? So MATH, right? In integer representation, in the Z26, the modulo 26 integer representation, MATH would become, so this would require some thinking. M would be, what value would M be? So A is 0, this is A. What is M? What is G? What is H? H is 7, L is 11, so M would be 12. What is T? T would be 19. Yeah. Okay. So uh, you represent m as uh, in 2 to the powers, it's 8 plus 4, so 2 to the 2 plus 2 to the 3, right? So it's 0, 1, 1, 0, 0. Yeah, A is A is 0, 0, 0, 0, 0. T is that one would be 16 plus 2 plus 1. So 1, 0, 0, 1, 1. And H would be 0, 0, 1, 1, 1. Right? So just giving this entire bit string 0, 1, 1, 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 1, 0, 0, 1, 1, 1. Right? And like the receiver knows that we need to divide this bit string into chunks of 5. So you divide this into chunks of 5 and you have these alphabets, MATH, right? So you don't need English per se. You only need zeros and ones. And that's how computers work. Like computers, at their core, uh, they only talk about they only use zeros and ones, sequences of zeros and ones to convey everything that you are seeing on your laptop or on your mobile screen right now. At the very core in the microprocessor, the the computation is happening among only zeros, strings of zeros and ones. Okay, can I explain it? So this is not related to the course per se. I was just trying to convey that in computer science, when you start studying theory, you'll see a lot more of just bit strings, like the mention of bit strings instead of English strings, right? So when we say we sentences, what I'm saying right now, I'm thinking in terms of SENTENCE sentence, right? I'm not thinking in terms of zeros and ones. So I'm thinking in terms of English alphabets. But uh, uh, computers, they actually think in terms of zeros and ones only because it's sufficient. And how I conveyed that it's sufficient uh, is by presenting that you can represent any English alphabet by a string of 5, a bit string of length 5, right? So a bit string of length 5 is sufficient to represent any English alphabet because there are 26 alphabets and there are 32 bit strings of length 5, 2 to the 5, right? So it's sufficient. It's sufficient in space to represent 26 alphabets because you can map, like you can map A to 0000, B to 0001, and so on, right? So thinking in terms of, so first alphabets to integers and then integers to bit strings. You can do this mapping. It's not that hard, right? So I did this for MATH here. So this bit string, this is MATH basically. So I could have just said, instead of saying math, I could have said 0 1 1 0 0 0 0 0 0 0 1 1 0 0 1 1 1, and like you could have interpreted that as math. So if you don't get this, it's okay, no big deal. But bit strings are important. Like it's enough, and you're going to see a lot more of that as you study more. Okay. So next question. It's a multiple choice question. What is the ciphertext of Corona using Caesar cipher? So I'm going to write the options. But I didn't tell you the shift. Okay, so you are assuming that the first one is F, right? No, 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 no. That was just the previous question. Uh, and somehow also the previous question. But no, not so in the first question the key was 6, so it wasn't 3. So key could be anything basically. Key can be an integer, modulo 26 of course, because 26 will get the same thing, right? Ah, okay, okay, sorry. I must have forgotten. Sorry. I'm really sorry. Yeah, you're right. Caesar cipher is where the key is always 3. So the answer is the D option, what you said. Yeah, you're right. I'm sorry. I take that back. Uh, yeah, so option D is the. And you can call me Karthik, not sir, because I'm not that old, even though I look. Uh, yeah. So the answer is FRURQD. Okay, good. Okay, so now we are going to a different kind of crypto system called the permutation cipher. Suppose the permutation is, so I'll just explain what a permutation is in case it's not clear to some people. Suppose the permutation is 1, 2, 3, 3, 1, 2. Now I'll move to the question later. I'll just describe what a permutation is. Oh, so we have studied permutations in school also, so I guess I don't need to say much about this, right? So it's like you have some sequence and you shift the positions, but the elements remain the same. So it's just a shift of positions, right? So here this is meaning whatever string you have. So you can have a string which has 3 positions, right? Any string x, y, z, and you want to apply this permutation to it. So you'll shift the first letter to the third position, so x to the last, second to the first, so y would become the first, and third to the second, so z would become the second. So this is the result that you would get after applying this permutation, right? So it's just a shift of positions, a rearrangement, an ordering. That's what a permutation is. And there are many ways to represent it. This is one way to represent a permutation. You could have also just said 312, right? Uh, that would have been well enough to understand that this is the permutation. Okay, I'm not going to say more about this. Now, if the ciphertext is A B C D E F, then what is the plain text? Okay. So first of all, the ciphertext has 6 letters, whereas the permutation was only for 3 strings of length 3, right? So the obvious approach would be to divide the ciphertext into, or the starting plain text. The starting plain text would also have been of length 6 because there is no length change in operation going on, right? So the cipher plain text would also have been of length 6, and you divide it into 2 groups of each of length 3, 2 halves, and you apply the permutation to both halves separately, and then you get the ciphertext. Similar to how the Caesar cipher, we have a string and BCA EFD. Yeah. So the answer is BCA EFD, right? Uh, so we'll divide this into two halves. So ABC. So ABC is the result, right? So the plain text should be CAB. Wait. Yeah, yeah, yeah. Hmm. Yeah, no, but I'm still confused. Like if the ciphertext is ABC, did I do something wrong here? Like how do I? You're right, but so yeah, it is right. But when I wrote this, what's the fault? What did I do wrong? When I wrote X. Yeah, yeah, yeah. So according to what I wrote here, it should be CAB, but it's wrong because the second position went to the first, right? So this should be the second. No, wait, again I'm doing something wrong. How did uh, the answer is supposed to be PCAEFD. So the people who are saying that as the answer, how are you thinking about this? Hmm. Hmm. Yeah, it's supposed to be something simple. I'm getting confused with something here. I don't know. So you start with BCA and you say that uh, okay, so the third should be the first should be the second, and the second should be the third, right? Yeah. So this is where you start and this is where you end. So I was thinking of it in the wrong way because I said you have X, Y, Z, and I was thinking that you take X to 3, you take Y to first, and you take Z to second, which is not right. The right interpretation of this is the third becomes the first, so Z would now become the first. First becomes the second, X would be second, and second becomes the third, Y. So now if you put A, B, C here, you can see B, C, A. Okay, yeah. So this is the so you that's how you don't see that one goes to three, two goes to one, three goes to two. No, third becomes first, first becomes second and second becomes third. So if you see this notation written somewhere, you have to be careful because I made a mistake just right now. Do not interpret it in the wrong way, right? I hope this is clear. Okay, so we'll move on to the final question for today. Number of possible keywords of length 5 in a Engineer cycle. Question. What are the, so there is a, how many, how many possible keywords are there of length 5 in a Engineer cycle? So for those of you who either don't remember from the lectures or just want me to repeat again, I'll just do it. What is a Engineer cycle? So it's like an adaptive Caesar cipher. This is just a name I'm coming up with, so don't write this anywhere. Just for explanation. So this is a modified Caesar cipher. So for example, in a Caesar cipher, if, let's say ABCD is the plain text, and there is a single shift key for the entire string. So every alphabet in the string is shifted by the same positions, the same key. The key is the same for every string in the alphabet, for every alphabet in the string. And for a Vigenère cipher, things are different. For this one, you can have different keys for each. So you can have two here, three here, five, eight, something like this, right? So A would shift by two, B by three, B, and so on, right? So different shifts for each position. You can have that, and that's called a Vigenère cipher. Now the way to this is generally denoted is not as 2358, but in terms of alphabets. So 2 would become B or maybe C because 0 is considering that 0 is mapped to A. 2 would be C. Yes. Yeah. No. 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 So this is not part of the question. I was just explaining what a Vigenère cipher is. So far, this is a digression. I'm digressing. I'm just saying what a Vigenère cipher is, and the actual question is how many possible keywords are of length 5 in a Vigenère cipher. So I'm not assuming anything else. I'm just assuming that the key is of length 5. So this, instead of being 2358, it's 5 lengths, 5 positions, right? So if I have a bigger string, I would split it into chunks of 5 each and apply the Vigenère cipher to each chunk, right? So in that case, how many keywords are there? So for example, one possible keyword is uh, A, C, D, E, K, something like this, right? So A here represents that A goes to A, C represents that A goes to C, so it's a shift of 2. This represents shift of 3, this represents shift of 4, yeah, and this to whatever. It's your own integer, right? So this is a shift of 0, A. So on first positions, you're shifting 0, second position, you're shifting 2, and so on. So this is one example. So how many possibilities, how many such keywords are there is the question. Hmm. Okay. Yeah. So the answer is 26 to the power 5. This is not very hard to see. So there are five positions, right? And for each position, there are 26 options. You can either shift by not shift at all, shift by 0, shift by 1, shift by 2, and so on till shift by 25. Shift by 25 is also a valid option. A becomes Z. But shift by 26 is same as shift by 0 because uh, A, if you shift by 26, you get back A. So there are 26 options and for each position, right? So it's 26 to the power 5. So this marks the end of our session for today. But someone asked me what's the demerit of a Engineer cipher. So it's not that different from a Caesar cipher. Yes, there are differences, but there are statistical attacks, very standard attacks that you can do against the Engineer cipher also. So all symmetric key crypto systems, or at least all ciphers that you're seeing here, are very vulnerable. They are not secure at all. But just to for teaching purposes, that's this is how we start when we start talking about cryptography. Okay. Uh, so this is the end. If someone has any questions, I'll be happy to answer. So there is a book by Cards and Lindell. I think that's a very good book, like for all levels. If you are a beginner uh, or if you are an expert or somewhere in between, it's a good book. There is also a book by Goldreich, but that's more involved. I'm not sure if on the board. Yeah, I'm writing currently. Can't you see on the this slide that I on my notes? Okay, so these are the books. I'll just write. Oh, book name. Okay, wait. I'll just Google quickly. We usually just remember the authors and wait, introduction. Goldreich. It's a Gold. Wait, I'll write in capitals. Goldreich. Oded Goldreich. Just to be complete. ODED. And Cards and Dildo. The book name is Introduction to Modern Cryptography. I think this the first one. Prefer the first one. Goldreich is more involved. This is better. Hmm. So that is what is used. Like most, if you have heard of the most, I'll just write here, RSA. So the most famous crypto system was proposed by Rivest, Shamir, and Edelman. The three of which got the Turing Award for this in 2012 or something, and they uh, invented this. So it's just a simple mathematical object that they came up with in the late 70s, early 80s. So that's when this RSA was developed theoretically. They came up with the theoretical definition and how it works. And this was the first, not the first exactly, but the first that actually is used, that came into proper use in the following decades. And now this is the most commonly used crypto system in the world. Like even for your any transaction, any kind of transaction that's happening online, RS is being used somewhere in there. RS is being used. Uh, yeah. Yeah. hmm So many. So what other examples? Like RS is the main. Knapsack also is something that failed, but like a good example to start. There is the Algamal crypto system, which is also very simple looking, not too hard. I don't think there are that many. Like especially in a course, the main examples that people teach are RSA, Algamal, Knapsack, not many else. Like the main mathematically involved crypto systems are lattice based crypto systems, and you won't be going into that, so don't worry. Like it's not that, I don't think it's that much, to be honest. Yeah. And yeah, so just to elaborate on the question a bit more, RSA is a public key crypto system. What it means is basically that every party, so there are two kinds of keys. There is the private key, or you can also call it the secret key, SK for short, and there's also the public key, or PK for short. So every party has an S key and a PK. In the Caesar cipher, for example, there is only one key, three, right? Which is just shift by three. But in a public key crypto system, every party has a secret key and a private key. So I would have a secret key, private key, and all of you would have your own secret keys and secret keys and public keys. And if a party A, which is usually called Alice, and there is a party B, which is called Bob, and Alice wants to send a message to Bob, Alice would use Bob's public key. Alice would only know Bob's public key and not his secret key. Everyone would know everyone else's public keys, right? So Alice would use Bob's public key, which is PKB, and send the message M in the form of a ciphertext. Ciphertext is using M and PKB, and then Bob can decrypt the ciphertext using his own secret key, which is not known to other people. So somehow the public key and the secret key are related in a way that encryption and decryption go through, and still like people are not uh, learning anything else about the message. It's a very magical thing if you think about it, and you will go into this later, like uh, in your course probably. So don't worry. So this is what a public key crypto system is. Who? What? Cryptanalysis? No, I don't understand. What do you mean? The bad guy. So the bad guy wouldn't know the secret keys, obviously, but only the public keys. Yeah, yeah. The bad guy will know the public key. The adversary, the one who's listening in, they will know all public keys, but still they won't be able to learn anything about the message from the ciphertext. So there is a definition for it. There are ways to define this, like how to properly define, mathematically define security, or not learning. not learning anything about the message, it's a non-trivial thing to define, and you'll see that in your course later, probably. Okay, so that should conclude our session for today. I hope you guys learned something, and see you next week. Bye bye. Thank you. Yeah, thanks. Bye. Yes, you can join the next session. In fact, I forgot to mention you should join the next session because it covers some different questions. Yeah. Thank you. Bye bye.